Very good morning to all the participants. As Professor Kumarwal already mentioned that the focus of this talk is going to be on grid integration of electric vehicles, and more so in the context of renewable energy integration, which means how this EV integration will have its interaction um, with the grid in the context of renewable energy integration. How does it affect or support or potentially support the renewable energy integration in a power system? So I think this introduction, I am assuming you would have been already given over the past couple of days. So I'll just skip this. That EVs are actually going to come. They're coming. They have been there in several countries. More importantly, if you are not aware of, there are some prominent countries have which have been actually experiencing this EV integration for a while. um, uh, Norway is one of these pioneering countries who have been, having this electric vehicle policy focus for a long time now, much earlier than several other countries. Denmark, a lot of activities have been happening over the more than past decade in EV space. Germany is one of the very active country. Netherlands is the other active country in EV integration. UK is also quite active, and some states in US as well are also quite active in EV integration. As has been the case with renewables, China came a little bit late in the EV space, but they have been very aggressive in EV space. So therefore, China is kind of one of the leading markets in the world in EV space as well. Okay, so this I'm assuming you would be already knowing that we'll have different AV sectors in this down the line, and which include electric vehicles, plug-in hybrid electric vehicles, and then we also know that we have different chargers, EV chargers involved, which can be classified into different categories, depending on the different characteristics. One of the classification is given on this slide. You can see here we have this level one, level two, level three, and DC charging. Um, and there are other categories also. For example, you have if you look at the Indian scenario, we have this Bharat AC 001, which has three guns, 230-volt AC. We have Bharat DC 001, and we have several others. For example, not in India, in general, at the global level, we have CCS chargers, we have CHAdeMO chargers, which is bidirectional, and we have other fast charging options available in EV space. In addition to that, we have several standards involved in EV sector, both in EV charging, at the connector level, as well as at the EV SC level, charging station level. And in addition to that, we have um, regulations and policies, which are very important fundamental component of any technology intervention in our society. So EV policy, for example, in India, we have a lot of focus on EV policies currently. Several states have already, either at draft stage or at the final stage, already given have EV policies. Others are also working in that direction, and the focus is currently now on. So first is policy. What comes first is policy. Then, based on policy, the technology intervention starts happening. But then, along with technology intervention, there is always a need for regulation. So the next very important aspect of any technology intervention is the regulation, and same is true here. We have EV regulations, which are there already in other countries. Those who are quite active in EV. In India also, we are now moving towards the direction of having EV regulations. Of course, we have guidelines from Ministry of Power, but EV regulations are also being is also one of the focus now in Indian EV ecosystem. So now, when we talk of EVs at the mass level, we have to think how, because it is a paradigm shift from conventional source of energy in transportation sector to the electricity sector. So what does it mean? The load is being shifted from conventional source of oil, gas in transportation sector to the grid, electricity. Now you have to uh, put things in perspective. We are already experiencing renewable energy integration at a rapid pace, which is changing, uh, which is introducing several challenges in grid operation, handling of these renewables. Now, along with that, we have this another major um, shift happening in transportation sector, where we are moving from conventional mobility to e-mobility, which means this load is also getting transferred to the grid. So there are two now major transformations happening more or less now in parallel. Of course, renewable energy is little bit mature, renewable energy integration, while as EV is has come relatively late. But both the actually transformations are happening in the grid, and it becomes more challenging to handle these two transformations simultaneously. Though the pace is the rate at which the two transformations are happening in the grid are relatively different, but nevertheless, the two transformations are happening parallelly, simultaneously in the electrical grid. What does it mean? We need to understand how potentially it can impact or introduce challenges in the grid at the aggregate level. Now we are not talking about a unit electric vehicle level. Unit electric vehicle is a drop in the ocean. It's not going to disturb the grid in any way. But when we talk about EVs at higher penetration level, then we have to, this same story has been there with renewables. Initially, post 1970s oil crisis, uh, Denmark and Germany, who are the pioneers in wind, started putting up wind turbines. A lot of policy interventions happen. Most of the people started putting up wind turbines in their backyard. But that was not a concern for grid operator at that point in time, because the percentage of these renewables was quite low. Same is true with the EVs at lower penetration. If it is the penetration is low, it is not a matter of concern. But when we are looking ahead, considering the policies and the targets that governments uh, would set or have set, or the market potential market emergence in the space, we have to consider the aggregate impact of these electric vehicles at the grid level. Now, if we look at that, so what could be the influences or impacts of electric vehicle integration at the grid? There are, of course, some positive, I mean, visible positive impacts, which is known to everyone. But there are also adverse impacts, or you can say challenges, that these electric vehicles can introduce in the grid operation. Not only increased power demand, that is very obvious. Harmonics power quality will be affected, because again we are introducing more power electronic converters in the system. It can actually affect the low voltage. It can affect the voltage profile in the distribution feeder. More importantly, depending on what type of charging you have. Do you have a dump charging? Do you have smart charging? Do you have coordinated and controlled charging in a feeder in a given EV fleet, or do you have controlled and coordinated smart charging strategies in place? So, depending on all those factors, this EV integration can actually introduce several challenges. It can introduce transmission congestion, distribution congestion. It can increase the increase the losses. It can actually affect the lifetime of the grid components, for example, transformers. So several other issues. It can actually necessitate um upgradation of the distribution infrastructure. For example, Delhi is bringing up this EV policy. It has not bring. It has already EV policy. Now they are focusing on enhancing the EV charging infrastructure. Now, when you talk of uh, upgrade, not rather actually building EV infrastructure, you have to think a lot on which type of chargers we should have, which type of charging stations we should have in the distribution system. For example, if you go for fast charging devices, chargers only, fast charging options only, what does it mean? One is it will increase the connected load to the grid, to the distribution feeder significantly. Second is, if you have these fast chargers more, let us say 22 kilowatt, and if you go on, on really on higher side, CHAdeMO charger, minimum 50 kilowatt, uh, then now imagine the aggregate connected load of these many chargers, fast chargers, and distribution system operator may not be the distribution system infrastructure may not be actually able to accommodate these fast chargers. You may have to upgrade the distribution feeders. Therefore, you have to uh, adequately devise this policy or the tendering process such that, or regulate the tendering process such that those EV chargers which the grid infrastructure cannot handle immediately should not be encouraged from the grid perspective. Of course, those who may think from market perspective will have the counter argument, but I am talking here from the grid perspective because it will necessitate uh, enhancing the distribution system infrastructure. Not only that, the protection of the distribution system will get affected. You have to now consider that as well. So therefore, these aggregating these electric vehicles at a large scale need a proper planning and thought process, uh, both short term and long term planning, as to what type of chargers, what type of charging infrastructure we should have in place such that we are able to accommodate this charging infrastructure uh, more adequately. And of course, down the line, you have to actually, you cannot stop market from being introduced through these developments in the technology, particularly in any new technology, which is the case with EVs. There's a lot of development, rapid development happening in EV infrastructure as well, EV charging infrastructure as well. For example, most of the new electric vehicle models that are being launched have now DC charging provision. It was not the case in earlier EVs. So therefore, you don't have the control over the market here. The electric vehicles that will come on the road down the line are going to have those features. And this fast charging is going to become a necessity because you may not want to wait for hours together, 7 hours, 6 hours to charge your electric vehicle, particularly when you are actually traveling from a little bit longer distance. You may need a fast charging device. So therefore, uh, this how these different charging infrastructure of different characteristics, fast chargers, slow chargers, home charging, public charging, private charging infrastructure, how does this affect the distribution system is very important to understand. And uh, the intervention or the introduction of or the built up of this EV charging infrastructure should be aligned accordingly. At the same time, at the grid level, you have other set of challenges. It is going to increase the demand on the grid. It is going to increase this power electronic interface devices in the grid. It is going to um, impact, rather actually increase the peak load, because the problem with the uncontrolled charging, more importantly home charging, is that the maximum charging, for example, particularly for home electric vehicle for home charging, is in the evening, which coincides with the peak. And now, if you are in, as we learn, hopefully in some of the slides, this increasing the peak load is something which the grid operator would not like to see, even in the worst case as well, because the better utilization of the grid infrastructure is in having as low as possible this peak to off peak uh, load ratio, demand ratio, or you can say average demand over a daytime or one day should be as much flat as possible. So therefore, all these things are there, which need to be taken into account to look at how the grid operation will be affected by these electric vehicles. And then also look at what could be the countermeasures, because often it so happens that the source of the problem turns out to be opportunity to address the problem itself. I'll give you an example. Wind turbines and solar PVs are or have been thought as the source of the technical issues, for example, which includes the voltage issue in the grid as well as the frequency. Now, you can actually use the same set of devices, that is power electronic interfaced wind turbine generators or solar PV power plants, to actually support both voltage and the frequency of the grid. So what does it mean? The source of the problem is being used as a solution to the problem. Of course, with several tools in the control and infrastructure, that is a side discussion. Same is true with electric vehicles. It introduces several challenges in the electrical grid, but at the same time, it also offers opportunities for grid support to stabilize the grid in a manner which has not been possible earlier, or which would not be possible without electric vehicles potentially. So what are the I think we already talked about. So there are different possible issues that these challenges that these electric vehicles will introduce, which include the stability related issues, voltage, frequency stability, power quality related issues, and to some extent reliability issues also. Now, what are the factors that we should consider while assessing the impact of EV charging loads on the distribution system? One obvious parameter that we need to consider is EV penetration level. How much is the EV penetration level? More the EV penetration level, more it will have the impact. EV usage pattern. This is very important. What is the usage pattern? Is it normal office going vehicle in the morning, leaving from the home, going to office and coming back in the evening, and then charging overnight? Or is it a commercial fleet of vehicles which is running throughout the day or probably throughout the night as well? Or is it public EVs? So accordingly, you have to actually, this usage pattern will differ, and then that will have accordingly the different effect on the distribution system. Household energy demand, of course, it was this particularly home charging goes side by side with the household energy demand as well, and distribution network capacity, which I already mentioned, which is also very important. So you can add more and more electric vehicle to the distribution feeder without any proper control strategy, charging control strategy. until it reaches its congestion point. You cannot add beyond that. The other option is, if you are having the smart charging strategy, you can actually control the charging of different electric vehicles connected to a given distribution feeder, and you can potentially have more electric vehicles connected to the same distribution feeder if you are controlling the charging strategies of these electric vehicles in a better manner, or in other words, if it is a controlled or smart charging strategy. This is one of the simple case study we did here at IIT Bombay on the impact of EVs on the distribution feeder. So this is the this is the distribution feeder. We have distribution loads, and we have different nodes where we are connecting these electric vehicles, and we are trying to see the impact of electric vehicles on the distribution feeder. This is the load pattern of different loads that are connected. Sorry, this is the demand at different nodes that are connected to this distribution feeder. And you can see here what we did is, this is, if you look at this network, ND1 is starting from the transformer side. So obviously, the node on the transformer side has a better voltage. So this is very intuitive compared to the nodes which are, this is a radial feeder though, compared to the nodes which are connected away from the transformer.
Yeah, contact.
So same is, I mean, this, as we increase the EV penetration, you can see the pattern is same. The pattern of the voltage profile is same, means being highest at the node connected to this substation, and being lowest at the node connected to the farther end of the distribution feeder. And on the other hand, what we can observe from here is, with the increase in EV penetration, the voltage profile is getting affected. The voltage is going down because the load is increasing. We took now two cases here in this simple study on impact of EV integration on the distribution feeder. In case one, we started connecting electric vehicles one by one from the end of the feeder. And in case two, we started connecting electric vehicles from the start of the feeder, that is from the substation side. And we kept on increasing the electric vehicles till we reached the other side of the feeder. Now you can see the difference here. Of course, at no penetration of EVs, the voltage is same at a given node. But as we increase the EV penetration, the voltage profile in case 2 is better than the voltage profile in case 1. The reason being simple. If we start connecting electric vehicles from here, it will draw the current, additional current. Of course, load is fixed, the normal load. It will draw additional current for this electric vehicle load only for this portion of the feeder. The rest of the feeder will not carry the current drawn by the electric vehicle. So accordingly, the voltage is not getting affected. Now, if you connect the same electric vehicle at the end here, now the current drawn by this electric vehicle has to travel all along the feeder, which means that since the current is traveling all along the feeder, the voltage drop is going to be more. I mean, in simple terms, voltage drop is going to be I. If we look only for the drop in simple terms from the electric vehicles, I electric vehicle into whatever is the impedance of this this distribution feeder. So that is what we can observe from here. if we are connecting electric vehicles from the start of the feeder, then we will have a better voltage profile compared to the case where we are starting this electric vehicle integration from the further end of the feeder. Now, we also try to see what is the impact on the hosting capacity of the two strategies. Now, hosting capacity in simple terms here would mean how many electric vehicles of the identical capacity or identical electric vehicles we can connect to this distribution feeder without overloading it, means without congesting the feeder and without violating the voltage beyond the acceptable value. So two factors we have to consider while assessing or estimating the hosting capacity of electric vehicles for a distribution feeder. One is it should not congest the feeder. Second is the electric vehicles should not bring the voltage down below the acceptable range. Now look at this case where we are trying to see the hosting capacity from the end of the feeder. In case 2 where we are starting electric vehicle integration from end of the feeder. The voltage is going down as the EV penetration is increasing, which is very expected, and the loading which is on this y-axis is increasing again as expected, and you can see the bottleneck. If you look at the voltage level, bottleneck is if you take 0.95 as the minimum voltage level, bottleneck is reaching here because voltage is hitting now the minimum allowed limit. Of course, we can change it. This is in this particular case we took 0.95. So therefore, you cannot go beyond this much of electric vehicle penetration. Now, if you do the reverse, you start connecting electric vehicles from the end of the starting of the feeder. Now you can see same bottleneck reaching here. The bottleneck of violating the loading, that is congestion or the voltage, is at this point that's 24 compared to 18 here. So what does it mean? Connecting electric vehicle charging points more strategically mm, is going to allow you uh, having more hosting capacity compared to if you are randomly or reverse order connecting these electric vehicles. This is about the losses. Again, I think this is intuitive. Losses will be more in case first where we are connecting the we are integrating electric vehicles from the end of the feeder because the current will travel through the feeder and therefore I square or losses will be more in that case. I think this is just little bit dynamics of it. We introduced a fault in the distribution feeder, and this is the current drawn by the electric vehicle. You can see that initially it was zero point 0.3 charging, and now it hit at 0.6 charging. The reason being it was actually we had treated in this particular case this EV as a constant power load here. Uh, so it was not, let's say, constant current charging in this particular case. This is the other study on impacts of this hybrid electric vehicles, plug-in hybrid electric vehicles. Again, a distribution feeder is taken here, and the impact is actually studied on this peak load, as I was mentioning, and the peak to average ratio. Peak load to average ratio is actually taken as the metric to compare the results. As I mentioned earlier, peak to average ratio or peak to off peak ratio should be as flat as possible, as much flat as possible. That is ideally unity in that case, which is not possible practically. So look at this. We have winter load here and we have summer load. So the load duration curve, the daily load curve is given here. The study is assuming different penetration level of electric vehicles 11%, 35%, and 45%. And of course, there is a base case without any electric vehicle connected to the distribution feeder. What you see here is, in the case of without any electric vehicle, you have the minimum of peak load, that is here. While as you increase the electric vehicle penetration, this off peak load at 11% is here. Peak load at 35% is increasing, and with being highest EV penetration considered in this study. So what does it mean? It is increasing the peak load, which is also increasing the peak to average ratio. As I highlighted earlier, why this happens. Losses, again, as expected, will increase with the increase in EV penetration. Similar is the case with the winter load, both with respect to this peak demand as well as the losses in the system. So what does it mean? It increases the losses. It is increasing the peak load, which is also, can potentially affect the lifetime of the distribution feeder components, particularly transformer. And then the results are tabulated here, summarized here. You can see here, this total losses are increasing, and peak to average ratio, for example, I think that is very visible from these plots. We probably don't need to spend time here. Now, having little bit understood the impact of electric vehicles on the distribution system, let us try to understand now how these electric vehicles, which are affecting the distribution system or the transmission system in different ways, be it increasing the peak load, be it increasing the losses in the system, be it increasing the overall demand in the system, be it affecting the power quality of the distribution system, and to some extent at the transmission system as well. Even the power quality is more of a concern at the distribution level. So now we need to understand how these electric vehicles can be potentially used to address these issues. Not only these issues, how we can use them to increase the accommodation of renewables in the grid. So, as I was highlighting in the beginning, now can we think of taking this electric vehicle integration as an opportunity to help us integrating more and more renewables in the grid? That's what precisely we are going to understand in the remaining time. But before going to that, how electric vehicles can support the grid in terms of increasing renewable energy penetration or supporting other, providing other grid support services, I will just give a little bit brief background of renewable energy integration. I'll not go into detail of it. I am assuming that you are familiar with it, but still I'll cover some basics of it for those who may not be familiar with it, such that we can put in perspective when we talk about electric vehicle support to the grid. So there are two aspects of stability in the grid. One is frequency stability and the other is voltage stability. This is simple analogy of the frequency stability where you have the brittle plate. So I'm not going into the technical definition, but rather I'm trying to put an example which can put things in perspective and make it understand that what does frequency stability mean and what does voltage stability mean. It is a brittle plate which is being pulled down by the load, means one force, net force by the loads, and being pulled up by these generators. Or in other words, the whole electrical network, electrical grid is pulled by two torques or two forces. One is electrical torque and the other is whether one is torque by the generator electrical and the other is load torque. Or two forces, one is by the generators which are forcing in opposite direction, and load which is forcing in opposite direction. If there is an imbalance between this generation and load beyond a point which is going to be determined by the strength of the grid, this brittle plate will simply break because there is no flexibility whatsoever in this brittle plate. Because of the imbalance in the equilibrium point between generation and load, this brittle plate is going to break beyond a point, which is very narrow band. That is precisely the case with the frequency of the grid. Frequency of the grid has to be ideally close to 50 hertz, practically within a few millihertz of 50 hertz in India and 60 hertz in other parts of the world, in US and others. That means the frequency parameter has to be within a very narrow band. We cannot afford to have larger deviation of frequency. One of the fundamental requirement of the grid is that at each and every instant, when I say at each and every instant, it's not a second, it is literally at each and every instant, the generation must balance the load. If the grid fails to match this generation and load at any instant, the grid is potentially going to collapse. There is going to be system outage. There is going to be blackout. So therefore, one of the fundamental requirement of the stable grid operation is that generation and load must match at each and every instant, even if it is in a dynamic state, even if there is disturbance. It doesn't matter whether you are operating it under steady state condition or there is a disturbance in the grid, the load and balance must match at each and every instant. That is the case with the frequency stability. And the frequency is a global parameter. For example, whatever is frequency in steady state condition is, whatever is frequency in Calcutta will be same in Mumbai. Whatever is frequency in one part of the grid, it will be same in the other part of the grid and steady state conditions. So it is a global parameter. While as in case of voltage stability, it is balanced similar scenario. The only difference is now the load, the force which is pulling this sheet on one side is the reactive power load and other side is reactive power generation. The difference is now this plate or the sheet is little flexible, rather more flexible compared to this brittle plate. And in the frequency case, you do not have an option to have the frequency below, let us say 47.8. It will vary from the grid to grid depending on the protection settings. For example, let us say in simple understanding, below 47.5, 47.8, even dynamic conditions hertz, the grid cannot survive. So the minimum frequency that potentially you can achieve is 47.8 in the worst possible case. I'm just giving an example. So therefore, beyond that, grid will simply collapse and the frequency will simply go down. Go down to zero. While as in the voltage, that's not the case. At the location of fault, you can have even in the worst case, severe most fault, you can even have a zero voltage if it is a dead short circuit. You can even have a zero voltage for a short time. That's not the case with frequency. You cannot have a frequency 20 hertz or 25 hertz for a short time. No, the grid will be already gone by that time. By the time you will let the frequency go that low. While as in the voltage, you can even afford to have the zero voltage in case of dead short circuit for a short time. So there is that flexibility in voltage stability, and also this reactive power balance has to be more importantly done at the local level. It is a more local balancing than the active power generation balancing, which can be done at the at the entire grid level. But even though we see this flexibility is more in case of voltage stability, okay, reactive power dictates the voltage stability. It is the reactive power which is the source for voltage control. So voltage stability has everything to do with the reactive power at the transmission level system. While as in the frequency stability, everything has to be done with the active power generation and load. Now, one may think now this is more flexible, so therefore blackout is more likely to happen because of frequency stability. But the opposite is true if you look at the historical background of all the blackouts that have happened so far. More blackouts have happened because of the voltage instability issue than the frequency stability issue. Okay, having understood basic concept of frequency stability and voltage stability, let us now try to understand how the grid maintains the stability when there is a disturbance in the grid. That is where we will introduce the ancillary services, and then based on that we will come to how electric vehicles can support the grid. Let us say we have this 50 hertz frequency. Grid is operating under normal conditions till this point. All perfect till the instant of the disturbance. Now suddenly there is a generation outage at this instant. But let us say, for example, in Indian grid, there is a 500, 800 megawatt generation outage. It is unplanned. There is a fault, the generator tripped, or there is a maloperation of the protection, the generator tripped. Unplanned outage of the generation. What did I say earlier? The fundamental requirement of stable grid operation, secure grid operation is that at each and every instant, the generation and load must balance. Now, please, those who are not familiar with this, look carefully here, pay attention carefully here. How does things happen at the onset of the disturbance? Now, once the disturbance takes place, we lost the generation, 500, 800 megawatt, whatever capacity. Load is not going to change. Load is same. The Now what should change? Ideally, the generation should change. But for the generation to change, to match the load or to match the deficit of loss of the generation, it will take its own sweet time. Governor control, which will actually in those generators which do have a margin, of course, first it should have a margin. The governor control will kick in only after 2-3 seconds, because governor control works based on the frequency of the grid, on the speed of the machine. So what will it do? It first needs to detect the change in the frequency in the grid. Then it needs to send the signal to the controller, governor controller. And then governor controller will send the signal to the command to the steam valves. If it is steam power plant, steam valves. Steam valves will open through the servo motors, which will take it is time. There is a time constant associated with all this, and then power plant will actually start increasing. Not that instantly it can increase. It will start increasing the power if it has a margin. So if it is a 100 megawatt generator, conventional power plant, which is operating at 90 megawatt, means it has 10 megawatt margin. This will typically start reacting to the frequency disturbance at 2-3 seconds from the disturbance, and then it will start increasing. Let us say uh, it was at 90 megawatt. It has a 100 megawatt here, and it was operating at 90 megawatt. The disturbance took place, and it will take 2-3 seconds to respond, and after that it will start increasing its output. That is how it will happen. But what did I say? Generation is lost instantly, in no time. 800 megawatt we lost in no time. load is same. Generation is not increasing instantly. Then the principle that we understood of balancing generation and load at each and every instant is violated here. But the grid will not collapse vertically. So therefore, we have to understand what is happening at the onset of the disturbance, which is making sure that this generation and load balance is ensured before the governor kicks in and before it increases, before the generators start increasing its generation output to compensate the deficit of generation due to the loss of the power plant. What will happen here? Because of the loss of the generation of 800 megawatt in this particular case, this is an electrical circuit. At the end, you have to see the grid as an electrical circuit. It has different generators connected in parallel, and it has a load. Let us say now we are representing the entire load as an aggregate load. This is load. Load is constant here in this particular case, and we lost one generation. Let us say it was supplying I1, this was supplying I2, this was supplying I3. So we lost this I2. Since the load is constant, it's not changing instantly, this I1 has to be electrically, I mean, that is the law of the circuit. So it has to be shared by these two sources. So what does it mean? The remaining generators, by the natural laws of electricity, will get overloaded. So what does it mean? They will get overloaded. The electrical torque experienced by the generator, the electrical torque which is on the stator side, experienced by on the rotor eventually shaft, experienced by this generator, which has been before the disturbance balancing this mechanical and electrical torque, this will increase now. So it will be more than mechanical torque for a given generator, which is still connected to the grid because of this overloading. Overloading compared to what it was supposed to generate, not literal means of overloading of the machine. Because of the higher electrical torque compared to mechanical torque, as I mentioned, cannot change instantly. Electrical torque can change instantly. That is the beauty of electricity, and that's why these loads are shifting from different sources, other sources of the electricity. It is fast, the control is very fast, the transportation is fast, it is more efficient. So that is what precisely is happening here. By the very natural characteristic of electricity, this electrical torque is changing instantly. But mechanical torque cannot change. What does it mean? The machine is getting more burden. Since it is a synchronous machine, it what will happen? The speed of the machine will start slowing down. The speed of the machine will start slowing down. Since it is synced, it is synchronized with the grid frequency, which is this in this case. P is a fixed number of poles. So the speed of the machine will go down. Means it will slow down the machine because you are putting more load. It is, I mean, it's very simple. If you are running with some load or without load or with some little load over your shoulders, and someone puts more load on your shoulders while running, your speed is naturally going to slow down. That's what is happening in synchronous machine. So because of the decrease in the speed of the machine, what will happen? The frequency of the grid will decrease. That is what precisely is happening here. The frequency of the grid is decreasing because of the change, decrease in the speed of the machine, which happens because of the additional load, electrical load getting shifted to the remaining generators, which are still connected to the grid. Now, before the disturbance, it was operating at synchronous speed. Let us say rotational speed is omega s. Before the disturbance, the energy stored the energy stored in a particular generator, let us say it was E1, is 1 by 2 j omega s square. J is the moment of inertia of the machine, omega is the synchronous speed. Now, as the speed of the machine went down, its frequency went down, let us say at this instant, we have here it was omega s, now it is omega 2. So E2, now the energy associated with the same machine is 1 by 2 j omega 2 square. What does it mean? The rotational energy that was stored in the machine has decreased from E1 to E2. So there is a change in the energy stored by the machine in its rotational energy, which is nothing but E1 minus E2, which is 1 by 2 j omega s square minus omega 1 square. What does it mean? This energy that was lost by this machine, because it is going to have now less rotational energy in it, this energy is actually inherently released to the grid. The change in speed which decreases the rotational speed of the machine and accordingly the rotational energy stored in the machine is being released to the grid at the instant, immediately at the instant of the fault, starting on at the onset of the disturbance. And it is this energy which is inherently, there is no control whatsoever. This all happens inherently because there is a magnetic locking between the rotor poles and the stator poles. As the machine speed goes down, the grid frequency falls down. So this inherent release of energy by the machines at the cost of the decrease in the speed of the machines is what precisely balances the generation load before this governor control kicks in. So in the initial few seconds, 2-3 seconds, from the onset of the disturbance, it is this rotational energy which is released by these rotating machines to the grid balances generation load. As I mentioned earlier, if that does not happen, the grid will collapse ideally. Theoretically, it will just collapse. But it is this rotational energy, which is known as inertia, which most of you, I assume, would be knowing. This is inertia. This rotational energy released from this machine to the grid inherently on the decrease in the speed of the machine, or you can say on the following the loss of the generation, is the inertia which these rotational machines release to the grid. This is the natural beauty of these synchronous machines that we have been having in the grid all along so far. They have this inherent characteristics of supporting the grid. This inertia is released inherently. You are not having any specialized controller for machine to release the inertia. Inertial response comes naturally in these synchronous machines. Same is true with reactive power. If there is a fault, a synchronous machine can supply 7 to 8 per unit short circuit current. That does not happen in power electronic interface renewables. This natural inertial response does not happen in power electronic interface renewables. And it is this inertia, then later on the governor starts kicking in, and then it starts increasing the power depending on the ramp rate of the generator, and then this inertia comes, that the speed of the machine comes back. Okay, so once this governor kicks in, after 2-3 seconds, the frequency is brought back to the new steady state value by this primary frequency control, this steady state value. But it is not necessarily going to be the value before the disturbance of the frequency. Now, when you talk about control, you have to think of two things here. One is a controller, which controls. Second is the source for the controller. You need a source of control. What do you want to control? For example, in a water tank, you want to control the flow of the water going through the tap, going out through the tap. You can control the water flow only if there is a water in the tank. If there is no water in the tank, your control will be of no use in that particular scenario. Same is true here. We have the primary frequency controller, which is automatic, but it's a controller. It is a man intervention control. It is a manual controller, which is manual in the sense it is being actually introduced a supplementary controller in the machines. It is not inherent. So this primary controller frequency control needs the active power to control it. That active power should be there, and that active power available is known as reserve. It is a backup power which should be available with the generator. Then only, as I was mentioning, it is 90 megawatt. If it is operating at 100 megawatt, it cannot release the power. It doesn't have the margin. It doesn't have the available power with it. So that available power is known as reserve. In addition to the normal power dispatch, the available power is known as reserve. For primary frequency control, we need primary frequency reserve. Then comes the secondary control after the steady state value is actually achieved. Secondary control has two functions. Primary control has only one function. Primary role is to stabilize the frequency at new steady state value. Secondary control has two responsibilities. One is it has to bring the frequency back to the nominal value or at least pre-disturbance value. That is the first function of the primary controller. Secondary controller. Second responsibility of the secondary controller is to release the primary control reserve. This 90 megawatt, 100 megawatt plant, which was operating at 90 megawatt, release it now. I'm giving you an example. Release it now 10 megawatt. So what does it mean? It is now operating at 100 megawatt already. What if a new event happens now? We don't have the margin available. So therefore, to make these generators which are participating in primary frequency control ready for the next possible event, we have to release them from the primary control. Means they should come back to their earlier generation, in this particular case 90 megawatt again, such that if there is a new event happening, it should again be ready to release this 10 megawatt to the grid. That is precisely what this releasing the primary reserve means. So secondary control has two functions. One is it should bring frequency back to the nominal value. Second is it should release the primary control reserve, which means secondary control reserve should be more than primary control reserve. If primary control reserve is, let us say, 450 megawatt, secondary control reserve may be actually 500 megawatt, because it will release this entire 450 megawatt, and also it may need that 50 megawatt to bring frequency back to the nominal value. Then comes tertiary control, which is slow controller. It has again two functions. So it has primarily only one function here. One is, which is actually to release the secondary reserve and maintain the frequency at the same value. That is how this frequency control and corresponding these reserves come into picture when you are controlling the grid, frequency of the grid. And we call this primary frequency control, and corresponding active power reserve is known as primary frequency reserve. Secondary frequency control, corresponding active power reserve is secondary frequency reserve. Tertiary control, corresponding reserve, active power reserve is known as tertiary reserve. And this is what precisely brings us to the ancillary services. Ancillary services are additional grid support services that the grid operator would need to maintain secure and stable grid operation. To accommodate, to cope up with the possible contingencies and other imbalances in the grid. Even after perfect scheduling of generation and load in advance, in real-time operation, you are not going to have a perfect balance. So to maintain that balance at each and every instant that I have been talking about, you have to have backup reserves in the grid. You have to have backup active power and reactive power reserves in the grid to control the frequency and voltage, rather to maintain the frequency and voltage profile of the grid. These additional support services which should be available at the disposal of the grid operator are known as ancillary services. These are in addition to the normal power that is dispatched and is being billed for a given generator. So broadly, we can classify these ancillary services into three categories: frequency control ancillary services, voltage control ancillary services, system restoration ancillary services. But everything revolves around uh, balancing active power load and active power generation, reactive power load and reactive power generation. All the operation of the grid revolves around only these two things primarily. When it comes to the technical side, of course, there are economic aspects of it where you have to minimize the economics of the grid operation. That's fine, but technically all you have to think about is generation load balance, both active and reactive power. That's what is happening here. For frequency control you need frequency reserves. For voltage control you need reactive power reserves. System restoration or black start service is the third ancillary service, which is again a combination of active power and reactive power support. Because if there's a blackout in the grid, now you have to start the grid back again. You need some generators to maintain the voltage first, and then the other generators can actually come in. So therefore, this for system restoration, again it is a reactive power and active power support. But broadly you can divide ancillary services, grid ancillary services, into these three categories. In Indian scenario, I'll not get into too much details here. In Indian scenario, you have we didn't have much ancillary services. Actually, the focus on ancillary services came in the context of this renewable energy generation post to 2010, um, when there has been, that it has been felt that there is a need for ancillary services in the grid, because that would be actually required to account this renewable energy integration brings into the issues where you need more and more active ancillary service support. So that's where precisely the focus of ancillary service has been there in India lately, in the context of renewable energy integration. And we have primary frequency reserve. Normally, in a well-deregulated market, well-developed electricity market, these ancillary services are paid because they are voluntary services. There is a separate ancillary service market where you get paid for primary frequency support, where you get paid for secondary frequency support, where you get paid for tertiary frequency support. But in India, primary frequency support or primary frequency reserve is mandated by Indian Electricity Grid Code. It is not being paid for. But the other side of it we need to understand is, I mean, it might actually bring into the question, why should a generator keep reserve margin? Because it will result into the revenue loss for a given generator if it is not getting paid for it. So if I am able to have 100 megawatt generation, why should I generate only 90 megawatt? Because I am losing this 10 megawatt reserve energy that I could otherwise generate and get billed for. Now, in Indian scenario, what is actually being, how is this being actually ensured, that the generators are not allowed to overload it. The generators are not allowed to overload their generators. Therefore, in case there is a necessity, this primary frequency reserve, which is of 4,000 megawatt in India, is will be actually supplied by these generators by overloading the machine, the generator, for a short time. So therefore, this primary reserve is ensured through this overloading capability of the generators, but accordingly they are not getting paid for it. Secondary control is in the process of implementation. To some extent it has been implemented. There have been several pilot projects of automatic generation control already done in India. Um and the work towards implementation of this automated generation control is under process, but yet not all the generators are actually being required to participate in the automated generation control, but down the line it is expected that we will have full-fledged secondary control as well. Tertiary control in India we divide into two categories: fast tertiary and slow tertiary reserve. Slow tertiary reserve has been in place for now 2 3 years, maybe a little over that, through RRAS, uh, Reserve Regulatory Ancillary Services. This is slow tertiary reserve that is in place, but for slow tertiary reserve, only those generators, only central utilities, regional utilities, which are actually which come under C, whose tariff and all is actually regulated by CRC regulations, and are actually dispatched by regional this load dispatch centers, RLDCs, are only allowed to participate in this slow tertiary reserve from the unrequisitioned power. What does it mean? If it is a 500 megawatt generator, if it is scheduling 590 megawatt, sorry, out of 600 megawatt, if it is scheduling 580 megawatt, for example, means 20 megawatt, it was not requested from it. It was not actually able to sell that 20 megawatt. Then that generator can actually participate in RRAS using those 20 megawatt. Not that generator on its own can decide how much it can keep reserve available for the RRAS. And there is a payment mechanism for that. Fast tertiary, a pilot project has been done where some of the hydropower plants have been used in a pilot project in fast tertiary. So it is expected down the line we'll have the fast tertiary as well in the Indian grid. I think I'll skip this. This is understood. We are increasing the renewables, but all I want to highlight is because of displacement of conventional generators, we are losing the inertia in the grid, which we have been discussing earlier. Inertia is actually what helps the frequency stability in the beginning, and because of the losing this diminishing inertia, for the same disturbance, we will experience more frequency nadir, means worst case frequency, which means potential load shedding, and in the worst case grid blackout. So therefore this inertia is also very important, and we need to look at how the inertia will be actually this diminishing inertia will be countermeasured. This is again a study on the Irish grid, where you can see for more than 28% time the grid is insecure in terms of inertia. Same is the case with this ERCOT in US. You can see that with the increase in wind penetration, the inertia in the system is decreasing quite significantly, and this is an issue for the frequency stability. Same is the case with the reactive power. We are displacing conventional power plants by these renewable energy generators, which means we are displacing this reactive power reserve as well. And then this low voltage ride through issue is again related to the reactive power, diminishing reactive power. These renewable energy generators are required to comply with the low voltage ride through requirement, primarily to maintain the voltage profile in the system, which has been happily being maintained by the conventional generators. Now, if you are displacing conventional generators by renewable energy plants, you are also supposed to take the responsibility of this renewable energy generator, conventional generators that have been doing in the past. And this is one of the latest example of this renewable energy issue, that is LVRT issue here, which um, kind of led to the blackout um, in the South Australian grid in 2016. So um, So because of the storm in the southeastern grid, there were back-to-back 5 faults in the system and around 6 voltage dips that these renewable energy plants experienced. And the LVRT did not actually require to have back-to-back these LVRT compliance. So therefore, those renewable energy generators decreased their output power, which increased the import from the rest of the Australian grid through the tie line, and the tie line got overloaded. Tie line was tripped because of the overloading, and the grid was collapsed. Now that shows the issue with these renewable energy generators in terms of voltage stability. Okay, so having understood this background, what sort of services would be required to maintain the stable grid operation and increase the renewable energy penetration? We can now look at how these electric vehicles can actually take the active role in grid support services. So there is of course vehicle owner motivation. If you as an electric vehicle owner uh, have a battery in your vehicle, if it is, for example, there's a pricing mechanism where um, electricity price is quite high in the evening because of the peak load, and it is cheaper in the daytime off peak load. You may charge it during the daytime and release the power to the grid in the night at a higher rate. That is a motivation for the vehicle owner. So you may have some revenue out of it. Of course, there are concerns of the battery life and all. That is the secondary issue. What is the motivation for the system operator to take the support from these electric vehicles? These electric vehicles are already in the electrical energy system, and at an aggregate level, they are offering us grid scale storage. Why not to utilize that storage which is already there for a different primary purpose, for the vehicle, for the transportation? If it is already there and we can tap this large scale electric vehicle storage, battery storage, we can use that for grid support services, because it is at the end a fast source of the active power. And how you can do it? You cannot do it with single electric vehicle. You have to deal with lot of electric vehicles, EV fleets, to get this support at the grid level. And what sort of grid support services it can provide? As we already understood, frequency support services, voltage support services. Of course, peak shaving it can help in, and it can help in congestion management and other related issues. So you can have the control infrastructure accordingly. You have different aggregators, different fleets. For example, Ola, Uber, it has a lot of electric vehicles. Or even you have third party aggregators which have contracted with different users of electric vehicles, and then it promises grid to provide some support, and then it accordingly controls your electric vehicle depending on your comfort level. It can electric vehicle charging infrastructure without being electrical vehicle connected to it can actually support the reactive power. It is at the end a converter. If your converter has a capability, it can actually inject the reactive power to the grid. This is one of the case study we did in terms of voltage support from EVs, same system that we discussed earlier. Now what we did is here, we tried to get the voltage support from these electric vehicles. You can see this voltage profile here. In this case, it is better because we allowed these electric vehicles to participate in the voltage support. Similarly, you can see here, without voltage support at a given voltage node, and we took two cases earlier as described. Case 1, end of the feeder. Case 2, when we started integrating electric vehicles from the start of the feeder. And the trend is same here. The voltage profile is better. You can see here, the voltage profile difference is better because we are able to support the distribution feeder with electric vehicles. Similarly, this right side is the case with the voltage support. Left is without voltage support. You can accordingly see that we are able to increase the hosting capacity with this voltage support from these electric vehicles. Somewhat similar study is done on other distribution system with solar PV in it. And we also try to, in our system at IIT Bombay, we try to look at the frequency support as well. You can see inertial and frequency support. For the same system, for the same disturbance, this is without any support. The frequency goes significantly down. And then we have, in second case, with inertia support only, means df by dt basis support, we are improving the frequency. In second case, in the other case we took with droop based control, and then we took the with droop and inertia. Then with droop and inertia, we have the better frequency control, both in over frequency and under frequency cases, to demonstrate that these electric vehicles can support the grid in terms of the frequency. I think time does not permit here. I would have loved to actually discuss other aspects of grid support from these electric vehicles. I think because in the interest of time, we may have to stop here. But just before stopping here, there are some demonstration projects already have happened, or some are happening in the at the different actually countries. For example, this is one of the project where electric vehicles are providing the grid support. They are being given the command and being asked to change the electrical power. They are charging power depending on the command. So you can see here it is unidirectional charger, and they are being given command to decrease the power, increase and decrease the power consumption. So this is one of the demonstration project. There is one more, I think I have, yeah, this is one more demonstration project in Los Angeles, where this lot of electric vehicles were being used to support the grid. So all I want to highlight here is these electric vehicles are being foreseen as an opportunity for the grid operator to increase the renewable energy penetration and have the secure and stable grid operation. So with this, I would like to stop here, and in case there are any questions, would be happy to take up those questions before we wind up this session. Thank you. In case there is any question, you can type, or you can unmute mic and ask the question. Otherwise, then I think probably we should close this particular session. Professor Kumaravel, are you there?
Hello, sir. I think now I'm audible. Yeah. So, dear participants, any questions? Sir, I think I have some personal question.
Yeah, please go ahead.
Sir, we talk about that voltage stability as well as frequency stability. So, you have clearly mentioned that voltage stability is very critical than frequency stability.
Yeah.
So, now the term rack-off is coming up. Rack-off.
Yeah.
So, in the presence of electric vehicle, how severe this term rack-off in related to the frequency stability?
So this rock-off rate of change of frequency is dependent on what I was talking about, the inertia in the system. So this swing equation, now swing equation is only valid for synchronous machine, but even without that also, this rho of df by dt is dependent on how much inertia is in the system. If you have higher inertia in the system, you will have lower rho of. Because of displacement of conventional generators, this the inertia in the system decreases, and accordingly this rho rate of change of frequency values for the same disturbance increases. What is going to happen? I mean, how electric vehicles are also going to play a role here. More electric vehicles is actually probably going to increase the penetration level of renewables, because they will increase the load. Now the increase on generation will happen primarily on the renewables in the long run, not on the conventional generators. So they will further increase the renewable energy generation. So it means further decrease in the inertia in the system. Now this rate of change of frequency, we have to see it from different aspects. Having higher rho here, go to this frequency curve. Having higher rho means, quick fall in the frequency. Means if there is a higher rho, the frequency will fall quickly. That's what is happening here. In this particular case, blue case, where we have more renewable energy integrated, less inertia in the system, for the same disturbance we have higher rho, which means your nadir is more severe. So that is where the challenge is. Higher rho means higher frequency decrease, means potentially higher frequency nadir, and load shedding, under frequency load shedding, and other issue. Now how to look at this, how to address this? We can actually have this inertial support from different sources. One we call as this virtual inertia, or emulated inertia, or synthetic inertia, where these renewable energy sources are being provided with supplementary control, which detects the rho in the system, and then commands the generator, be it solar or wind, to release the power quickly into the system. That is emulated or virtual inertia. So that can to some extent actually address this lack of diminishing inertia. Now coming to electric vehicles. Electric vehicles are offering us, as I mentioned, grid scale storage. They can, as long as they are connected to the grid, they can also participate, technically speaking, in this inertial support. Having a appropriate controller in place, those electric vehicles can also support the grid through this inertia, and which means they can increase the inertia of the system and decrease this rho-off. The other issue of higher rho-off is also anti-aliasing protection. I will not go into details in that, but that is also other set of issue that this higher rho-off is actually introducing in this grid operation. So hope that answers your question.
Yeah. Thank you, sir. Thank you.
Hello, sir. Am I audible?
Yes, please go ahead.
Sir, my question is that we have seen in the past where because of the renewable energy penetration to our grid, there was a problem in California and all about duck curve and all. So how much of the problem will be our Indian grid will face when we are penetrating all these renewables and EV to our Indian grid?
So duck curve issue has been there because of particularly solar PV. You have this net demand decreasing as the PV penetration increases, particularly during the noon time when it reaches its peak value. So what does this duck curve do is you have a morning peak, and then off peak, and then evening peak. Now, because of this increase in solar PV penetration, there is this duck curve. It decreases net load, which is actual demand minus PV generation, decreases, and then the peak is not decreasing. Peak will be, let us say, assume same. Now, what is happening with this is the issue here is your net demand, which is actually demand on the non-renewable sources, is decreasing fast here. What does it mean? Let us look at this, the belly of the duck. The conventional generators are going to be least committed at this point in time because you will have higher penetration from solar PV. Let us say this is solar PV. So now in the evening, what is happening is solar PV is decreasing. Generation from solar PV is decreasing, but load is increasing. What does it mean? Now you have the ramp power requirement quite high here in the evening. Since you don't have many power plants, conventional power plants here, you cannot bring them quickly in the system. So therefore, there is a challenge of increased ramp up power rate at the evening peak here. When your solar PV generation is decreasing fast and your demand is increasing. In one of the studies in India, it was expected that if no countermeasures are taken, this ramp rate requirement may reach up to 32 gigawatt per hour. You can imagine you have to bring up 30 gigawatt of generation in 1 hour. That is a huge challenge. So, but the on the practical side of it, since it is a well-known and well-understood problem, this duck curve, I'm sure that the grid regulators and grid operators will take necessary countermeasures to ensure that the issues that are associated with the grid, this duck curve, are not going to be experienced in Indian grid. So that is my take on it. Hope that because it's not something new, emerging issue. It has been happened experienced by other grids. The problem is well understood. Therefore, while planning for higher penetration of renewables, the necessary actions would be actually taken in advance. Hope that answers your question.
Thank you, sir. It answers my question. Thank you. Thank you so much.
I think I found 2 more questions in the chat box. Shall I go ahead, sir?
Yeah, please.
Yeah, I think there is a question from Salit Tapasvi. She said, nowadays the number of EV increases. So what is the effect of harmonics on the grid?
See, electric vehicles are increasing, which means power electronic interface load. Now, of course, electric vehicle with bidirectional feature is a prosumer, but most of the time is, as of now, we have predominantly unidirectional chargers, EV chargers, so we'll just take it as a load. Since this electric vehicle penetration is increasing the penetration of power electronic devices into the distribution system, it is definitely going to increase the power quality issues, for example, harmonics issues. But having said that, we have a lot of learnings from renewable energy integration. So therefore, there are going to be standards, there are going to be regulations, there are going to be compliances with respect to the power quality as we increase more and more these electric vehicles. There will be limits up to what should be the power quality level at the output of the electric vehicles, which will limit the impact that these power quality harmonics may have on the distribution system. So I hope that should take care of the potential issues that this might actually introduce. As I said, we have a lot of learnings from the renewables. Hope that answers your question.
Thank you, sir. I think one more question. I think let me take it as a last question. Any additional circuit required to provide inertial support by EV?
Yes, it cannot. See, the inertial support, as I said earlier, in the conventional generators is inherent. That is, as I have told, is the beauty of these synchronous machines. Because of the magnetic coupling locking between the physical rotor circuits poles and the stator poles, there is inherent support that it provides to the grid in terms of inertia. But if it is an electric vehicle, we have this charger in between. Here is the electric vehicle. Here is the grid. Now, since you have this power electronic interface between the electric vehicle and between the grid, this, first of all, this is not a rotating machine. It is a stationary device. Second is, no matter what frequency is here on the grid side, it will not know. It is blind. It is blind from the grid. It is like look at the charger of your computer or laptop. It will say the range from whatever 100 volt to 240, 250 volt. Frequency also large range. It means it will draw the power no matter what is the voltage within that range, no matter what is the frequency on the grid. The computer will not actually see any disturbance on the grid side. That is precisely what will happen here. If this device, electric vehicle which we are talking, will not see, will not experience, will not understand there is a frequency disturbance in the grid, there is no question of releasing the power, additional power to the grid or decreasing the load. So for that, what you need to do is you need to have a supplementary control which will measure the frequency at the grid level or the grid side, and that frequency you will, let us say, compare with the nominal frequency, and you will say delta F here, and you have a gain here, and this gain will send the command. I am just explaining it in simple circuit. Will give a command to the electric vehicle that there is a decrease in the frequency of the grid and you need to increase the power or decrease the load. Decrease the load if it is unidirectional, or inject with the power if it is the bidirectional charger. Now, in the normal condition is this delta F is going to be 0. This signal is going to be 0. It will behave depending on what the charging state this electric vehicle is. But if there is a frequency disturbance, this command will accordingly go to the electric vehicle and it will accordingly decrease or increase the power depending on the disturbance in the grid. So we need this supplementary control, which we call as inertial control. This is simple explanation of that. I think it puts across the message, which in my opinion answers your question.
Yeah, thank you, sir. Though there are number of work has been reported in literature based on charging facilities and related to power electronic aspect of electric vehicle. So in my knowledge, limited work going on related to power system, means impact of electric vehicle and power system. I think our speaker of the day today, our Sakir sir, is one of the person who is actively involving in resolving issues related to penetration of EV into utility grid. So thank you very much, sir, for your valuable session. I hope the people who are working in power system will be more benefited. Really, I myself benefited a lot knowing some related issues, especially in terms of frequency stability and voltage stability, and how the tau curve is coming and creating the impact. So really, the session is very useful. Thank you very much for spending your valuable time as well as accepting our invitation. On behalf of all the participants and my own behalf, I express my sincere thanks to you. Thank you, sir.
Thank you very much, Professor Kumarwal, for inviting me. It was a pleasure to interact with the participants here, and I hope I was able to put across some message. Of course, time didn't permit to discuss more in detail, but I hope I was able to put across some of the messages that I wanted. I'll be glad to take any question offline in case you have any. Thank you very much. Thanks a lot.
Thank you, sir. Thank you. So, dear participants, with this we come to the end of the first session of forenoon.